Hello everyone, welcome to what will be pre-lecture 30. We're going to be talking about phase transitions in this pre-lecture. So this is something that on some level I'm sure you are all familiar with. If we think about our intermolecular forces we've been talking about, a big kind of observable property of those intermolecular forces are transitions between our states of matter. And so we have the different phases here, gas, liquid, and solid. If we go between a gas and a liquid, we're either evaporating or more generally vaporizing or having condensation. If we go between solid and liquid, we're melting and freezing. And then the tricky two to remember, just because you're probably less familiar with them, are sublimation and deposition. So if we go from a solid to a gas, that's sublimation. If we go from a gas to a solid, that is deposition. Okay, and we're going to spend this pre-lecture digging a little bit more into these. So first off, vaporization and condensation. Those are just our definitions for them. So again, condensation going from the gas phase to the liquid phase, and the opposite is vaporization, so going from a liquid to a gas. And the rate of the condensation when it is equal to the rate of vaporization, neither amount of liquid or vapor will change. And so this is something that we call a dynamic equilibrium. It doesn't mean that our liquid is no longer evaporating. It doesn't mean that our gas is no longer condensating. But the key here is that the rate of both reactions is going to be, both transitions, I should say, is going to be equal. Okay? So, like I just said there, the rate of vaporization is going to be equal. They're still occurring, but at the same rate. Because gases have pressure that they exert, we can measure a property related to this equilibrium called the vapor pressure. So if we have a sealed container with a liquid and gas in equilibrium, the pressure of that gas in that container is going to be something that we call its vapor pressure. Okay? To visualize this a little bit better, so a lot of text on that last slide, but say we start with just a liquid, if our time is equal to 1 here, if we started with just liquid, then if we have water, that water is going to start to evaporate. We're going to end up with water molecules in the gas phase, and as we get some water molecules in the gas phase, some are going to start to go back to being the liquid phase, condensating, if you will. Condensing would be another way to say that, while we still have some evaporating, and then eventually we're going to reach a point where our forward and backward, our evaporation and condensation rates are going to be equal, and that is when we would say we could measure the vapor pressure. Okay? So with vaporization and condensation, if we think about them in relation to intermolecular forces will impede vaporization. Strong intermolecular forces, I should say, will impede vaporization and will favor a recapture of the gas phase molecules as they collide with the liquid surface. And so if we have strong intermolecular forces, that means we should expect a low vapor pressure. Okay? On the other hand, if we have weak intermolecular forces, then our barrier to vaporization is smaller as we increase that kinetic energy, and the likelihood of recapture is less, and so we will result in relatively high vapor pressures. Okay? And there is a parakeet licking some condensation for your enjoyment. Another way we can think about this is in terms of kinetic energy. And so as our temperature increases of our liquid and our gas, our vapor pressure will also increase, because as we increase the amount of kinetic energy here, so you can see the x-axis on this graph is our kinetic energy. This is a graph that we've seen before. So another way to think about it is once we pass this certain threshold of kinetic energy, those molecules are able to enter the gas phase. So as we increase our temperature, we're actually going to increase the number of molecules with enough kinetic energy to transition from being a liquid to a gas. And so just a reminder, at any temperature, the average kinetic energy is what we're most concerned about because we have a whole range of kinetic energies that those molecules are going to have. And so again, when we raise the temperature, we're going to increase the average kinetic energy, and in this case, increase the number of molecules that are in the gas phase. Okay? All right, so that was vaporization and condensation. Next up is melting and freezing. And so if we start with a crystalline solid and we add heat to it, if we, in other words, increase its kinetic energy, then those molecules can gain enough kinetic energy to break intermolecular forces of the solid, and it will begin to melt. And so at this point, the temperature of the solid will stop rising, which we'll talk about more on Monday. Despite our continual input of heat, that energy is going to breaking those intermolecular forces, okay? And that will increase the temperature of the liquid. Then, as basically we reach another equilibrium where we are between our melting point and our freezing point. Something I will say here is that our melting point and our freezing point are the same temperature. The way we define it is basically just by which way we're going. So if we're adding heat, we're melting something, we would call that a melting point. If we're decreasing the amount of heat, we're freezing something. That's just semantics, basically. Okay? And this has a value. We call this the enthalpy of fusion. Again, our equilibrium between our solid and our liquid. This is an endothermic reaction when we are inputting heat, when we are melting things, and it is exothermic when we are freezing something because we're decreasing the amount of heat in our system. So hopefully you still remember those terms from about 2 units ago. Okay. Next up, we have sublimation and deposition. So these are kind of the weird ones. So if we go from a solid directly to a gas and bypass our liquid state, we can actually do that in a process known as sublimation. The reverse of that is deposition, where we start with a gas, and instead of it condensing into a liquid, it goes straight to being a solid. Dry ice is kind of the classic example that you're probably familiar with, where a block of dry ice is actually solid carbon dioxide, and so it is dry because it does not melt, and it sublimes. It will turn from a solid to a gas. Another example that I find quite pretty is the sublimation and deposition of iodine. So if we start with iodine crystals down here and start to heat them up, we get this purple solid turning into a purple gas. Fair warning, this purple gas is extremely toxic, so don't do this at home. And then if we were to cap our container with something like a beaker, we can see redeposition of the iodine as it goes away from the heat on the hot plate. It will deposit on the beaker, and we get those nice purple iodine crystals that look like that. Okay? So if we put this all together, we can create something called a phase diagram where we graph pressure against temperature. And at any pressure and temperature, we can find if something will be a solid, a liquid, or a gas. And we also have basically lines between those phases. So any line you see on here represents a phase transition. And so anytime we cross that line, say if we went between a liquid and a gas, that would be our boiling point or our point of condensation. If we go between a liquid and a solid, that is melting and freezing, and then solid gas is sublimation deposition. We do have this one point where all three lines intersect called the triple point, and it is actually where you have all three phases in equilibrium at once. And this is an example of a chemical called cyclohexene. At its triple point where you can see it's boiling. As it's boiling, it starts to freeze, and then basically we get that equilibrium between liquid, solid, and gas. Okay, so that's it for today. I hope that was helpful. If you do have any questions, please let me know. Otherwise, I will see you in class.